Swayam Prabha. Digital India. Educated India.
Good morning. Welcome to lecture number 13, part 3. In the lecture number 13, part 1 and part 2, we have discussed the construction, working principle and different types of expansion devices such as capillary tube, thermostatic expansion valve, that is TEV, automatic expansion valve, etc. So, we have made a comparison between the different types of expansion devices, comparing the certain features, advantages, disadvantages. So, in part 3, lecture number 13, and also in the next lecture, part 4, we will be solving some numerical questions based on the expansion devices. We will be seeing how to select a expansion device for a particular application. Let us move to the first question. Determine the incremental length of a capillary tube of inner diameter 1.63 millimeter, which will reduce the pressure of the saturated liquid refrigerant R22. The refrigerant used is R22 from a temperature of 40 degrees centigrade to a saturation temperature of evaporator of 5 degrees centigrade. If the flow rate of the refrigerant is 0.01 kg per second, the dryness fraction is assumed to be 0.21. So, let us solve this problem. So, though the detailed solution is given in the PPT, I will be solving the problem step by step, so that the learners can have better clarity. It's a quite lengthier problem. Let us write the given data given. The condenser temperature is given as 40 degrees centigrade. Evaporator, let us go to the problem. This is the condenser temperature, 40 degrees centigrade, and this is the evaporator temperature, 5 degrees centigrade. So, the pressure is reduced corresponding to a saturation pressure of 40 degrees centigrade condenser temperature and corresponding to a saturation pressure of 5 degrees centigrade, which is in the evaporator. So, evaporator temperature is 5 degrees centigrade. The inner diameter of the capillary tube is given. It is 1.63 millimeter. So, let us take as capital D, 1.63 millimeter. The dryness fraction is represented by the small letter x, that is 0.21. 0.21. So, we have to find out the incremental length of in the capillary tube, that is delta L. And mass flow rate is given. So, due to the system compatibility, so I have used M. Actually, it should be M dot. M dot is given as 0.01 kg per second. M dot is equal to 0.01 kg per second. Mass flow rate. So, let us solve this problem step by step. And the refrigerant used is R22. R22. So, the properties have to be evaluated for the refrigerant R22. So, the refrigerant is R22. Let me write it clearly. So, we have to find out the incremental length, that is delta L. Incremental length delta L. So, first we are going to find out the specific volume of the liquid refrigerant that is coming out of the condenser, that is before the expansion process or the throttling process. So, the refrigerant liquid specific volume before throttling. So, that I will be taking a small v. Since it is liquid specific volume, so the subscript used is VF1. If it is vapor specific volume, it will be VG1. Okay, so V1 equal to VF1. So I will be using this empirical relation. I will be using this empirical relation to find out the liquid specific volume of the refrigerant before throttling. So it is VF1 equal to 0.777 refrigerant liquid specific volume before throttling, that is before expansion process, before expansion or throttling process. So V1 is equal to VF1, which is equal to, there is a empirical relation. So it is 0.777 plus 2.062 into 10 power minus 3 plus 2.062 into 10 power minus 3 evaporator temperature. There is one more term, 2.062 into 10 power minus 3 into, this is, sorry, since it is before throttling, it should be condenser temperature, not evaporator temperature. So this will be TC. Okay, so this will be TC plus 1.608 into 10 power minus 5 T square, TC square. This will be condenser temperature plus 1.602 into 10 power minus 8 TC square. So divide by 1000. So let me check the equation, 1.602, 1.608. So 1.608 into 10 power minus, sorry, this is after, before throttling is here, before throttling, 1.608, 10 power minus 5, 608, so let me write it, 1.608 into 10 power minus 5 TC square. So this is the empirical relation which we have taken from the literature. This is for applicable for the refrigerant R22. It is applicable for the refrigerant R22. In case if the values are available in the tables, we can take it directly. In some tables, we will have only the VG value. Sometimes VF value may not be there, so it has to be evaluated based on the empirical relations which are found in the literature. This here TC is given 40. We can substitute the temperature in degree centigrade itself. So when we substitute, we will get V1 is equal to VF1 is equal to, so here it is 40. This is the condenser temperature which is given 40. Okay, I have substituted it. So 0.000885 meter cube per kg. 0.000885 meter cube per kg. Specific volume is the reciprocal of density. The density unit is kg per meter cube. So therefore, the unit for specific volume will be meter cube per kg. So this is the refrigerant liquid specific volume before throttling process. Okay, so we have found this as V1 equal to VF1 equal to 0.000885 into 10 power refrigerant liquid viscosity before throttling. So since it is before throttling, we have to substitute the temperature of the condenser, temperature of the condenser. So refrigerant liquid viscosity before throttling. before throttling process. So viscosity is represented by the letter mu. So since it is liquid viscosity, it is mu suffix F1. Small v is the symbol for specific volume. Mu is the symbol for viscosity. It is equal to, let me write the formula. The values substitution, since I have given in the PPT. So if due to shortage of time, I may not be able to substitute each and every value. Okay, so at least let me write the formula. 2.367 into 10 power minus 4. 2.367 into 10 power minus 4. This is the first term. Then we have got the second term. Minus of 1.715 into 10 power minus 6 Tc. Minus of 1.715 into 10 power minus 6 Tc. Tc is the temperature of the condenser. 1.75 into 10 power Tc. Plus 8.869 into 10 power minus 9. Plus 8.869 into 10 power minus 9 Tc square. So this will be the empirical relation to evaluate the viscosity of the liquid refrigerant. So when we calculate, you will substitute the value of the condenser temperature in degree centigrade. That is, here Tc is in degree centigrade. Tc to be substituted in degree centigrade. So it is given in degree centigrade. So 0.0001823. So this will be equal to 0.0001823 Newton second per meter square. So this will be the value of mu1, which is equal to the viscosity of the liquid refrigerant before throttling. 0.0001823. Let me check this value. So this is the viscosity of the refrigerant liquid. Now I am calculating a ratio of the mass flow rate to the cross-sectional area, that is m dot A. This is m dot. This is m dot A. So area is pi by 4 d square. So m dot A equal to m dot by A is equal to, this ratio will be used in the subsequent calculations. M dot by A is equal to m dot by area is pi by 4 d square pi by 4 d square. D is given. So convert the diameter into meter. So that will be 1.63 into 10 power minus 3 meter. Okay, so the diameter to be substituted. Mass flow rate is given 0.01 kg per second. So if you calculate, we will get, so this can be, so this is equal to 0.01 divided by pi by 4 d square. D is 1.63 into 10 power minus 3 square. So this ratio will get it as 4807.7 kg per second meter square. Kg per second meter square. M dot is in kg per second, area is in meter square, which is the denominator. So the unit will be kg per second into meter square. So this is 4807.7, 4808. Next, I'm going to calculate the velocity. We know that m dot is equal to rho AV. Rho is the density, A is the area, V is the velocity. So velocity will be m dot by A into V. So using that equation, I will be finding the velocity at the inlet. Velocity at the inlet. So this is m dot. So we know that m dot is equal to rho into A into V. This is the equation of continuity, where rho is the density, A is the area, and V is the velocity. Since density is equal to 1 by specific volume, therefore the above equation will become m dot is equal to area into capital V by specific volume. Let me write it here. V is the velocity and small v is the specific volume. Specific volume. This is in meter cube per kg. This is in meter per second. Meter per second. So therefore, from using this relation, we can find out velocity at, we can write this equation at the inlet and as well as at the outlet. So if you are writing as this one, at the inlet, m dot equal to rho 1, A will remain the same. So V1. So this will be V1 by small v1. Therefore, velocity at 1 is equal to m dot into V1 by area. That is what I have written here. M dot into V1, that is m dot by A into V1. So this is the specific volume. All these values are known. When we substitute the values, we will get the inlet velocity at 4.3 meter per second. So this value is given. This we have found out in that is the first step. Specific volume of the liquid refrigerant before throttling. Area is pi by 4 d square. So when you substitute the values, we will get 4.3 meter per second. 4.3 meter per second. Then we can find out the Reynolds number. So Reynolds number is given by the formula rho Vd by mu, where rho is the density, V is the velocity, D is the diameter, mu is the viscosity. Sometimes it is called as dynamic viscosity. So rho Vd by mu. So we know instead of rho 1, I will substitute the specific volume small v1, that is the reciprocal. Specific volume and density are reciprocal. So all these values are known. So we will find out the Reynolds number at inlet. So Reynolds number it is represented by the letter Re, Re1, which is equal to rho 1 V1 into D by mu1. Since rho 1 is nothing but 1 by specific volume. Therefore, this can be written as V1 into D1, or we can write it as D itself divided by mu1. This is the velocity which we have found. This is given in the problem, and one more term will come, that is small v1. This is the specific volume which we have calculated, and this is the dynamic viscosity. So when you substitute, you will get the Reynolds number at the inlet as 43,444. 43,444. 43,444. So next I will be calculating, once we find the Reynolds number, then we can find out the friction factor F. So friction factor is, that also I am finding at the inlet. Here the suffix 1 refers to the condenser portion, and 2 refers to the evaporator, that is before expansion and after expansion. So 0.33 by Reynolds number to the power of 0.25. So friction factor is equal to friction factor. Let me write it neatly. Friction factor 0.33 divided by Reynolds to the power of 0.25 or 1 by 4. 1 by 4. So this value is known, we have found out. So F1 is equal to 0.0229. 0.0229. So for the inlet, that is inlet to the expansion device, that is the outlet of the condenser is the inlet to the expansion device. So we have found specific volume, then dynamic viscosity, then we have found out the velocity. Using all these properties, we have found the Reynolds number, then we have found out the friction factor. friction factor. So similarly, we have to do the calculations at the after the expansion process, that is before the evaporation process. So refrigerant specific volume after throttling. Here I will be substituting the temperature of evaporator temperature. Before throttling, we have substituted the temperature of condenser. So here we have to substitute the temperature of evaporator, which is 5 degrees centigrade. So refrigerant specific volume after throttling process, that is VF2. So refrigerant specific volume after throttling. So here I am finding after throttling VF2. This is, if you substitute the value, the temperature of the evaporator in this equation, you will get this one, 0.0007877. Then I am finding the vapor gaseous state specific volume. So what happens during the throttling process? Sometimes during flashing, some liquid will will be converted into vapor. So we need to take as a two-phase region, both liquid and vapor. So the liquid specific volume after throttling is 0.0007877. The vapor one, this is the vapor one specific volume. So here there is a pressure term. Since we know the evaporator temperature, we can find out the evaporator pressure from the R22 tables. Corresponding to 5 degrees centigrade, the evaporator temperature pressure is 5.84 bar. So let us go to the table. So this is R22. This is 4 degrees centigrade. This is 6 degrees centigrade. So we have to take the average of these two. That will give the evaporator pressure corresponding to 5 degrees centigrade. So I have taken the average value. So this is the average value. So convert the bar into Newton per meter square. 1 bar is 10 power 5 Newton per meter square. Similarly, for it may be required. So corresponding to condenser temperature of 40, I have taken the condenser pressure, which is 15.3 bar. Let us go to the table. So this is R22 table. 40 degree is here. So the pressure is 15.341 bar. So now I am calculating the specific volume by using the dryness fraction. V equal to, there is a relation VF plus X into VFG. X into this, X is the dryness fraction. This VFG can be written as VG minus VF. So that's what I have written here. So since it is a two-phase region, we should know liquid specific volume as well as vapor specific volume. So the vapor specific volume we have calculated using this formula. So substitute the values. Dryness fraction is given. This is given as 0.21, which is given in the problem. And when you substitute, you will get the specific volume as 0.009127 meter cube per kg. So I will stop at this point. I will be continuing this problem and in addition to a few more problems in part 4. Thank you.